difficult to talk to all of you with just one small screen. Yeah. But I'm going to do this anyway, because otherwise we'll be short of time. And there's one important point I wanted to make about the coursework, because I tried to look at some questions that were asked on Friday, which I couldn't solve, just solve over the weekend. So I want to make sure that not too many people are stuck with this. Okay? So what we could do is, I will make this point about the coursework we are doing, that if you're going to get stuck, to get past that. And I will go through the options pricing part that we did on Friday, yeah, where I went through the whole thing that we were going to look at, looking earlier at the basic assumptions. And I said we'll go through slightly more detail now. Yeah. But I think I will try and catch up on that on Friday as well, to see that all of us are clear. So if you can't see this terminal, then would you mind bringing your chairs over here? Or this corner, over here. I know it's not very convenient, but you can go over here. Why does this not even set up the CVX? So this is like people collecting coffee and then standing immediately next to the coffee. Just keep moving. Okay, let's kind of assume this is reasonable. You can object. You can say that this violates some health and safety rule, and then we can go home. Yeah. Okay. So the point that I wanted to make about coursework, which I can't get because for some reason this is not setting up the CVX path, is that we were trying to minimize an error, something like this. One, yes. So when some of you tried this, you showed me that your results that even if you blew up tau to very, very high numbers, you were getting all the weights with some non-zero value. It wasn't looking sparse enough in some of your simulations. So this cost me half an hour on Saturday morning. And I think the confusion here is that you've got to look very carefully at what's on this y-axis. Yeah? If you had a small value of tau and you minimize this, you will get a solution in which all the weights are being used, or negative as well. All the weights are being used for very small values of tau. Yeah? But as you increase tau, there is no reason, if tau is very large, there is no reason for the model to care about the data error. Yeah? And the model will force all the weights to be very, very small. We never get identical zeros in numerical optimization. It will give you very small values. But if you try that without looking at what the values here are, then you get confused as I was for half an hour. Yeah, are you with me? Yeah? This is the problem in your code, right? You're happy now? Okay, so these are the guys who cost me half an hour. So just watch to see what happens here. Okay? Don't expect identical zeros, numerical optimization. This is a proxy for selecting a subset. It will give you a solution. We can work with that solution. It is not a perfect solution. Yeah, it's a suboptimal solution. But that suboptimal solution here is arrived at by solving a continuous minimization problem. And when you solve a continuous minimization problem, you will get answers that are not identically zero. So you will look for very, very small values. You set some threshold and zero everything below that. Okay, is that clear? Or has anyone got problems with this? Yeah.
Does W have to sum to 1? Will you set that?
Yeah, so this is what caused conflict between the constraint here, and if you go W transpose 1 equals to 1, then we had conflicts and this solver doesn't always solve it. So the suggestion to that is use this minimization purely to select And once you have selected, you can always normalize it. Yeah, that'll be a hack. Yeah, but we are happy to do hacks in our community, at least. Yeah. Oh, what have we done to you? Will any alarm ring if I open this? No? Okay. Yep.
In that equation, is that the L2 normal or the L1 square?
Yeah.
So this is L1.
No, in the...
Yeah, so it's L2 now.
Is it L2 normal square? Is it L2 normal?
I think it's L2 now.
Okay. In CVX toolbox, if you square it, it becomes a convex function, so I got an error saying it wasn't allowed, and I think that's what the original paper did.
Right, okay, yeah.
So I just used the L2 normal instead.
Yeah, that's fine, yeah. Okay, so that's the only point. Other than that, I think rest of it must be pretty straightforward. No? You challenge this view. Go on.
Well, test error is lower than training error.
Test error is lower than training error. Usually it should not be the case, yeah. But are you normalizing it correctly? Because remember, the error as a quantity depends on how much data you're testing it on. Yeah. So if you define it as root mean squared error, then usually you would expect the test error to be higher than the training error. Yeah, because training error you can fit it perfectly. Yep.
I just want to add to that point. I did get test error lower for one set of stocks, but then higher for every other subset of stocks I use. I got it higher.
Yeah.
But there are a few instances that it does happen.
So you, at the end of the day, when you work with real data, and you are a statistician looking at what happens across a lot of things, you can always have freak results. Yeah. The important thing is not to take freak results too seriously and make claims on that. Yeah. So this is why always, when some of you did the machine learning course, we always did multiple runs across cross-validations and quoted variants of results, not just a result. Yeah. Okay. So you have a few more hours to finish this, I think, or a few more days or whatever. In that time, I'm far away from Edinburgh. Okay. So one of these is the mouse that helps me. Okay. So let's get to what we were talking about in. This is even nicer because I forgot to throw this in here. Where was this? Does the pointer show on this? Well, I can point this way. Repeated complaints about the time it takes for the tutor's machine to respond have not been addressed. Yeah. Ideally, I would like the tutor's machine to respond much faster than the student's machine, so I can stay one step ahead of you guys. But no, they want everything to be the same. Anyways, this is wrong slide, isn't it? Oh, what am I doing? Okay, so with derivatives pricing, the key idea is that we are going to ask the question, what is a fair price of something at which me and one of you can trade, given uncertainty about what is going to be like at some point in the future? Yeah? And we are going to trade an object whose value in the future is determined by the future value of some underlying stock. Yeah, and this is what options contracts are. So I, say I have a bank and I'm a big, very rich guy, I issue a contract to you saying that at some point in future time, you can buy a particular share of this at a particular price. So your exercising of that contract means I'm obliged to sell at the price that I have signed in this contract. Yes, that's a call option. Equally, a put option is one where you have the right to sell at a particular price that I have undertaken to effect. Okay? So if you hold that contract, then you can come to me and say, yes, you promised to buy this Southampton University share at value 100, here is it, buy it. And then I have to sell, I'll give you £100 for this. Yeah, so that's a put option. So the question then is, at what price would you buy such a contract from me now? And if you were to buy this contract, what should I do? So that when the time comes and you're going to exercise it, I will be able to meet the obligation written on the contract. Okay? So that is going to happen in a world where the underlying asset on which this is written is going to change in time. Yeah? So both of us have to somehow agree that a fair price now is something that either of us cannot take advantage of and systematically make money. Yeah? So if I'm stupid and I always underestimate where this market will go, yeah, and you have knowledge of that, then you will exploit it. Yeah? And the other way around. So what's seen a lot in this literature are two things. One is somehow you need to model the dynamics of what's going on. And that modeling that way will give me a way of analytically price such products. That's the first thing. The second thing is we have this notion of no arbitrage, that there isn't a systematic way under these assumptions one party can gain an advantage. Okay? Once we have both those in place, there is a way to derive a closed form set of formulae that helps us price simple options, which are the European style exercise, no dividend paying call and put options. Okay, so that's slightly loaded statement. European style exercise means if I sell you this contract, you can only cash it on the date that's specified on it. Okay, non-dividend paying means that between now and the time of exercise, that underlying stock is not paying a dividend. Yeah, that the stock price is just moving stochastically by trading. Okay. What was the other one? European style exercise, non-dividend paying stock, and the interest rate is assumed to be constant throughout, yeah, which is also a forced assumption, not real. So it turns out that under these specific assumptions, and Black-Scholes were the guys who solved this famous Black-Scholes formula comes about. You can price these call and put options, European style exercise, non-dividend paying, constant interest rate. Okay? So that's the first thing that we need to learn. How do they do this analytically? The second thing is then we recognize that the analytical solution comes under very specific assumptions. And these assumptions may not be held. So we need alternate ways of pricing options or futures contracts which may not satisfy the simplistic assumptions that we made. So what we do, we go to numerical methods. And when we go to numerical methods, what we try to do, the process of developing such algorithmic frameworks, is to say, can I invent a numerical method that would exactly match the closed form solution when these assumptions are held? Then I'll be a little bit comfortable that this numerical method I've invented is a reasonable one. Okay? And on that numerical method, I can impose other types of products, price other types of products, by saying such assumptions that I made do not hold. Okay? So we will look at three things. One is the standard Black-Scholes formula, which is, you can't live without it. It's so widely used. It's assumed everybody knows this. Yeah. We will look at two types of numerical methods. One is binomial tree. So we'll say that a stochastic process that underlies this Black-Scholes equation, you can precisely approximate this by walking on a binomial tree of a particular type. Then the question, what happens is that that binomial tree will have three variables. How much do you move up? How much can you move down? What's the probability with which you make either of those moves? Okay, we say there is a probability with which I make an up move, 1 minus the probability I make a down move from the stock price at any given time when I go a little bit. Yeah? We can match those probabilities of movement and the amount by which you move up or down precisely onto the unknown parameters of that stochastic continuous time model. The continuous time model is characterized by a drift, it's characterized by an interest rate, it's characterized by a variance, volatility. Those three could be matched precisely by some relationships onto the type of walk I will make on this binomial tree. Okay? If you had that, then you can say this binomial tree can precisely model this continuous time pricing problem or formula, whatever. Okay? And then the third one we will learn is doing things by simulation. So you can have this stochastic process I have written, yeah, and say, let me simulate sample paths from this. So from this point in time, the value next would be a slight drift plus some random perturbation. So I would simulate a random number and make this perturbation. So then I can say, oh, one sample path would have been this way, this way, this way, this way, up to here. I do this again. I do this again. I do this again. Yeah? So if I did this many, many times, over all those sample paths, I get at the end of the time period of interest, a distribution of what this would have happened, what would have happened. Okay? And based on that distribution, I can make some statements about pricing. Okay? So that's the idea. When you start using this idea, we'll hit a few mathematical algebraic tricks. We will hit a few tricks that have to do with sampling. If you want to randomly simulate data, what are the tricks that are involved? And we will learn a bit of those in this part of the course. Okay? Is that clear? When we go into... This still doesn't work. That's not to be expected because I just pulled this out. Yeah, so it's not the fault of this one. Okay, never mind. So let's just go through a little bit slower than I did on Friday. What are the little tricks that are here in pricing options by the Black-Scholes formula? Okay, this is what we'll do now. I think this is the right time for you to start opening a book. The Black-Scholes way of pricing options is written about in 100 different, maybe 1,000 different places. But the textbook by Hull is perhaps the most famous. It's the textbook that's used by, I don't want to say Bible, but it's the book used by everyone. Okay? The best I can do is to show you how these things are derived, try to explain to you how one goes from one step to the next, what are the assumptions, what are the ideas. But if you go and open the book, there is text written between these two equations here. And that's really important. It's only by reading it that you will get it more. Okay? And so if you're not here, but that's the wrong thing to say because those who are not here are not here. If you're not here and only stare at the slides, you will never learn. Okay? And so if you know people who are not here, you should tell them this. Okay, so this is one of the cool things that we learned about the use of this no arbitrage constraint. That's the put call parity. So we looked at this last week. We said, suppose we had two portfolios. One is a portfolio consisting of a call option and a certain amount of cash. Yeah? And the other is a portfolio consists of a put option and one share of the underlying stock. It turns out that in either case, at time t, whether the stock price is greater or less than the strike price, it turns out that I will have the same value of my portfolio. Yeah, and that's that argument all of you should be able to understand. This just straight from the definition of what these options are. At time t, if the value of the stock is bigger than k, then in portfolio 1, I will make that much profit. Yeah, and I already have this much cash. Therefore, this is the value I have of my entire portfolio. And the next one, if S of t is bigger than k, then the put option is worthless. I will not exercise it. Yeah, and I have the stock in my portfolio. That's the value of this. And the same argument for what happens when you have a down. In both cases, I will have a portfolio of value k. Okay? And this no arbitrage argument says if that were true, then right now we should think that both of them should have the same value. Both these portfolios should have the same value. Yeah? So that immediately fixes a relationship between the put option value and the call option value. Given the risk-free interest rate, the time to maturity is the same, and the strike price is the same on both these. Okay? So if someone were to write a call and put at a particular strike price at a particular value, then it turns out there will be a forced relationship between those two. So if you know the price of one, then the other one is determined by this. Yeah? Then comes the question of how do we model the dynamics? Yeah? The model that's used to model dynamics of stock prices is geometric Brownian motion, which is for the purpose that people think that things are moving at random. And if I model it in this particular way, it captures the fact that there might be a drift, that's over a period of time, things might grow, things might not stay constant, but grow up a bit. And the fact that there is stochasticity in this, yeah, and different stocks might have different levels of volatility, so this sigma might change, yeah, and there is this random disturbance. Okay? The question that then gets asked is that if you think that a particular random variable follows that kind of a motion, that kind of a random motion, what can you say about functions of that variable? So this is the fundamental question. So we think that an options price is related to the underlying stock price. So it's a function of that underlying stock price. Yeah? So it turns out there is in stochastic calculus the fundamental result coming from Ito's lemma that if a process is like this, then a function of this follows a particular structure. It satisfies certain constraints. Yeah? If you knew the increment of an underlying process, then you can write the increment on a function of this, and that increment on the function of it depends on how this changes in time, how sensitive is that to the underlying variable, this one. Yeah, so it's a partial derivative of the function with respect to this underlying variable, and it also depends on the second derivative. Yeah, and that second derivative with respect to any variable, usually you should imagine as something relating to diffusion. Yeah, so if you think of, I don't know, if I smoke here, and the smoke slowly diffuses in this medium, nobody is pushing it to go anywhere. It's just diffusing by random movement of little molecules. Yeah, and that process is a diffusive process. There are three things that come into that. So you can think of it as a spatio-temporal process because it varies in space. And if you sit in any corner and look at the intensity of smoke, it's a function of time. Yeah. So if you think of the concentration of smoke from my cigarette as a function of both space and time, then I can talk about how it changes with time. So partial derivative of the concentration with respect to time. I can talk about partial derivative of how the concentration changes with space. Yeah, I would be interested in that because its concentration is very high near my cigarette and very low far away. Yeah, so that I can talk about a gradient between this one and that one. Yeah, I can also, at any local point, talk about the second derivative of the concentration with respect to space. And that is a term that hits all the time when people analyze diffusion. Yeah? And that hits us here as well. Okay, so the first result we use to apply that is to look to see if I make this geometric Brownian motion assumption, what might happen to the log of this underlying thing? I'm perfectly entitled to ask this. Yeah? And if I ask that question, it turns out that in order to apply Ito's lemma to ask how much would this increment for a corresponding increment in the underlying thing, it turns out I need three terms. Yeah? This comes from Ito's lemma that I'm going to apply later. Oops. Okay. And the terms that I need are how does this, what's the time derivative of this? What's the derivative of this with respect to the underlying variable on which this is written? And what's the second derivative? Yeah? All these three I can calculate for log. Yeah? And if I did that, these are the simple terms. I go and plug that into Ito's lemma, which tells you what's the relationship between a change in S and a change in F. Yeah? Turns out I can just go substitute and I derive an expression that tells me a result that's useful. And that result is that log of this variable has a normal distribution whose mean and variance are writable like this. with me? So I made some assumptions about Brownian motion of some underlying stock. It turns out whenever I go and look at this process, the log of that process will have a normal distribution. And its average would be somewhere here, and it has a variance here. Intuitively, you can kind of say that the mean should be higher than where it was initially, because I have assumed a little mu, yeah? And it will go up by mu times t, yeah? What's less intuitive is that why should that be penalized by the variance? Yeah? If it fluctuates a lot more, will it not go up? Maybe it comes down on average. Yeah? That's a little bit intuition loses because it's log of that is what we are looking at. Yeah? That's slightly intuitive because that says the variance, how much I would expect it to fluctuate, will increase with time. Yeah, so that kind of makes sense. So there is algebra that tells you this is exactly what would happen. Our brain says, yeah, maybe that looks reasonable. Yeah, at that point we are happy. Yeah, at that point I say you are happy. So that's okay. So what else can we do with this? Yeah, so this is where the Black-Scholes model comes from. What they argue is that you make this assumption about the process, you look to see that you write the most general thing that says the change in option price is going to look like this, and then ask the question, what might be boundary conditions? So if we say we are going to price a call option, we can say at time t, that is when the option matures, yeah, then we have a solution for the option price. We know precisely what that is going to be. It will be the largest of the difference between st and k or 0. If st is smaller than k, then the value of this function is going to be 0, yeah, because the call will not be exercised. If it's bigger than k, then I get a linear payoff. This difference is my payoff. Okay? So whatever happens between now and then, or now and t, when you hit t, I know something. Yeah? And I'm going to use that in solving for the way things are going to change, or what it should be now. Okay, so where does that come? So what we could do is start with a portfolio. So here's the way you link this thing that we learned about no arbitrage against, couple that with this dynamical model. So suppose we take, we buy delta stocks, yeah? And then I sell a call option. So on Southampton University shares, I'm going to say, I'm going to sell you a call option, which tells you that, gives you the right to buy from me at time t, Southampton University shares at price k. This is what I have written. Yeah? So then what I have to do is between now and time t, things are going to change. Yeah? So in order to service that contract, I might think I should buy one Southampton University contract and hold on to it. Yeah? So at the time he's going to exercise his contract, I can give it back to him. Yeah? So we can push that argument and then say, suppose I own delta stocks and I have issued one call option. What might the relationship between them be? Yeah? So here is the value of this portfolio. Is this correct? So the portfolio that I have has this value, which will be delta times the value of S at any point in time. Yeah? Take away the value of the call option. Yeah? At this time t. What might happen? What's the change in that? D of pi. So that little portfolio where I have bought delta stocks and sold a call option is going to change in value little by little. It's going to change because it is written on the underlying thing, which is going to change. That's the S. Okay? The S process changes. Therefore, the pi process is going to change. And Ito's lemma tells us that the change in d of pi, I'm going to write it like this. Yeah? And this bit is the change in, so the delta sits here. Delta times ds is that bit. The rest of it comes from d of f. And I've just collected the term corresponding to d of s in here. Yeah? Somebody says, Mr. Ito says this is how it works, then I just go and write it down. Okay? If I then look at this one, then I say the little portfolio I have with some stocks and selling of shorting a call option is going to be something that changes with time with the way the call option price might change, with the second derivative of this one, with the function of the stock, this one minus this one, times DFS. That DFS is a nasty thing. And this is what always underlies any stochastic thing. The change that happens to that underlying stochastic random variable is something I can't quantify, I can't write down. Okay? So all my uncertainty about how this portfolio that I hold might change is in here. Okay? So the trick that I might do is to say, suppose the amount of stock that I hold in order to be able to service this contract is the same as the way the option price might change with the way the stock price changes. Yeah? If I choose delta to be the same as partial derivative of f with respect to s, then it turns out in this changing portfolio value, the stochastic term will disappear. Okay? So that is, underlies that is the idea of hedging. That I think I have written a contract, I think I need to keep an amount of stock to be able to service that contract, and the amount, and I'm scared about uncertainty of doing this, and because I'm scared about the uncertainty, what I would do is, if I'm clever enough to hold enough stock which is the same as the way the stock price, the option price might change with respect to the stock price, then I'm safe. My life is deterministic. Okay? So that seems to make sense, because then nobody can deterministically make money, right? So the equilibrium that we hit in that should hold, right? So if I take delta to be this one, because delta is, I have freedom over delta. This is what I bought to be able to service this contract. So if this is set to that one, then it turns out that the stochastic term will disappear, and the resulting portfolio is going to be riskless. It has to be deterministic. Yeah, so I don't pay any risk because I have cancelled out the random part. So if I cancel out the random part, then I can argue the growth of my portfolio should be the same as the way money would grow in a risk-free market. Yeah, same as holding on to some bonds. Okay? So that of course is R times the value of the portfolio times the increment of time, where R is this interest rate. Okay? So if I push that argument a little bit more, I just pull out the algebra, I equate what I bring from here to what I bring from here. And what I would have written is a partial differential equation which hasn't got a stochastic term in it. Okay? So the underlying world is stochastic. By pretending that I am capable of holding a portfolio where the amount of stock that I have bought is the same as the way this underlying option price might change with respect to the stock price, if I think I can do this, yeah, then it turns out that I have a differential equation that's no longer stochastic. And the clever thing with Black-Scholes model is that those guys showed you can solve it. They have this equation, differential equation, which has second derivative with respect to time. We know about the boundary conditions, which for the call and the put, and these two guys very clever guys solved it. Yeah? And the solution happens to be a formula like this, and in that formula, all the things we have, we can identify. There is a cumulative normal function over here and here, which we know is the integral from minus infinity to the current value of interest, the Gaussian distribution. Yeah? So this cumulative normal function is like a sigmoid, right? We have seen that. It goes from 0 to 1. Yeah? At any point, the value of that is the integral of a Gaussian from minus infinity to that point, is the area under this one. Yeah? So that's known. We are comfortable with this one. We are comfortable with things like square roots. We are comfortable with things like log. We are comfortable that R is interest rate that we know. Sigma is the variance term, which is the volatility, if we say, which we perhaps can estimate from data. And then K and T are written in the contract. Okay? So everything about this set of this equation is known. So we plug this in and we get a value for this call price. With me? Yeah? So now if you went and read whatever the book by Hull, you should be able to understand this. Any questions? Yep.
I still don't understand how the other part is risk-free.
Why is it risk-free? So it's deterministic. So initially when we did the portfolio model, we saw variance as risk. Yeah? Why did we say this? We said we buy something, we hold on to this, and this thing might change in time. But there is some reason to believe by observing, say, historic behavior, that at some point in time, it's going to have a probability distribution with a particular mean and variance. Yeah? And that variance, we said, was going to be risk. Where did that notion come from? That notion came from it being uncertain. Yeah? So uncertainty is risk. Yeah? And if the uncertainty is high, then the variance is high, and we said the risk is high. Yeah? So here, in the development of this model, we saw that there is the only source where we can pinpoint uncertainty is the way the stock price might change, the DFS. Yeah? Okay? So if we constructed a portfolio, which is the pie that was constructed there, and we look at how this pie might change, d of pi, and so that's the portfolio I've constructed. It's going to have a change. That change can be decoupled into a term that depends on the uncertainty, and the rest is known, deterministic. All of us will see the same. Yeah? So if I cleverly construct this portfolio so that the stochastic term cancels, yeah, then there's no risk. That's the argument.
The DFDS part,
Yeah.
how is that determined?
Right. So now comes the little bits here. So how do we say that this one is not random? Yeah. But this is a functional relationship. Yeah. So if you took this one, this as the solution, if we took C is the f, that's the call here, is the function. If I differentiate this one, this whole thing with respect to S, you and I will get the same answer every time. Yeah, it's a functional relationship. Yeah, the call option as a function of the underlying stock. What is its derivative? Yeah, which is not the same as asking how that underlying thing might change. Yeah, how the underlying thing might change is stochastic, but we cancel that out by a judicious choice of pi. With me? The idea of taking this, I think now you guys have to start reading. This has to do with the notion of hedging. So what I have done in constructing this portfolio is, remember I started by telling the story by saying I've sold you this contract, and then you're going to come back to me, yeah, at time t to exercise this contract. So what I then have to do is to hedge my, that's the term hedge, my risk against you exercising that contract. And the way I would do that is to say, oh, suppose I can buy that much stock and hold it, then there's no uncertainty. Yeah? And if I were to hold this, then the price that you expect to pay for the option and the price at which I'm willing to pay you the option is the same. There's no arbitrage there. Yeah? So that delta hedging can be taken a lot further. People work with these terms, these derivative terms, also in hedging, yeah, of various ways. There are, I have forgotten what these terms are called. There are, so the delta is, of course, we know, delta, yeah. One of these terms is called a gamma, another is called a beta, I believe. And in the financial market where people are not that civilized, they refer to all these variables as Greeks. Yeah? Because Greek symbols are used to represent these variables. Yeah? And there are lots and lots of trading strategies that are based on optimizing these, on using these, and so on. We'll look at a few of them later when I get around to finding what they are. Okay? But yeah.
On the board, you seem to find D1 and D2 is the same thing, but then you find D2 as D1 minus.
Oh, okay. So I think I missed a minus sign here somewhere. I think that should be a minus. Yeah. I think the first one and the last one is correct, and it's left as an exercise to the reader to figure out what I got wrong. Yeah. Okay. So that's the basic idea in Black-Scholes. The only thing you need to know, or you need to have intuition of, that is the methodology involves playing with assumptions about what the dynamics might be, and then working out if that is the stochastic dynamics. There is theory that tells you what is the dynamics of a function of that random variable. Yeah? And if you can relate those, then you can get started. And if you can get started, and the judicious choice of this cancelling the stochastic part gives a deterministic equation, some guy solves it, he comes up with a closed form solution. Okay? So that's the main thing. So what I might do is I might stop there instead of going any further about the next one. But what we will go in detail on how to price options on a lattice on Friday again. I touched on this last week, but on Friday we'll do this. I'll perhaps go through this rather fast because you can already see what's going on. And then I'll go into simulation-based methods. Okay? And I think I can't let you have more than a few hours between the deadline of the first coursework and the release of the second one. I think I have a very, very tough coursework set already, but I haven't word processed this. So I think we can do that on Friday. Yeah? Okay, yeah, sorry about the mess of moving around, but if you have logged in, you want to log out. Yeah. Yeah, sure.
So I get the results, something like this.
Yeah, yeah.
And then